everyone, and welcome to the M2L31 series Level 1 training course. Today, we're going to take a look at one of the peripherals inside the low power domain of the M2L31 series, the Low Power I2C. First, let's start with an overview of the I2C communication interface. I2C stands for Inter-Integrated Circuit, and it's a very common communication protocol used to exchange data between multiple chips. I2C only needs two wires. One is SDA, the serial data line, which carries the data. The other is SCL, the serial clock line, which provides the clock signal. Both of these lines are bidirectional, meaning every device on the bus can both send and receive data. On an I2C bus, you can have multiple masters and multiple slaves, so the design is very flexible. Because both SDA and SCL use an open drain structure, you must add pull-up resistors. These resistors pull the lines back to a high level whenever no device is actively driving the line low. So in summary, I2C is a two-wire, bidirectional communication protocol that uses open drain outputs with pull-up resistors, allowing multiple ICs to share the same data and clock lines for communication. Now let's talk about how I2C is actually used in real products. It's a protocol that works really well for low-speed data transfer, so you'll see it in a lot of common peripheral devices. For example, things like double EEPROMs that store system configurations, or G sensors that detect movement and tilt. Almost always use I2C. Temperature sensors are another very typical example. They rely on I2C to report the system or ambient temperature back to the MCU. And even audio-related components, like Nuvoton's audio codec chips, often use I2C for configuring their internal registers. So in short, whenever you need a simple and reliable way to exchange small amounts of data with sensors or configuration devices, I2C is usually the go-to choice. Now let's take a look at the differences between the regular I2C and the low power I2C in the M2L31 series. The first big difference is that the low power I2C almost supports the 7-bit addressing mode. Next, its clock source can go up to 24 MHz, which is more than enough for most low-power applications. Another key point is that the low-power I2C works together with the low-power PDMA to move data around. That means the CPU doesn't have to step in all the time, which helps reduce power consumption. But the most special part is this. Only the low-power I2C supports auto-operation mode when it's running as a master, and that lets it automatically handle data transfers even while the MCU is in a low-power mode. So it's extremely power efficient. In a complete I2C transaction, you can think of it as going through 4 main stages. The first stage is the start condition. This is how the master tells the slave, "We're about to begin communication." When the SDA line moves from high to low, while SCL is high, that creates the start condition. The second stage is the address plus the read-write bit. Here, the master sends the slave address along with one bit that indicates whether this transaction is going to be a read or a write. The third stage is the data transfer. This is where the actual data moves. Either the master sends data to the slave, or the master receives data from the slave. And finally, we have the stop condition. This tells the slave that the communication is done. When the SDA line goes from low back to high, while SCL is high, that generates the stop condition, and that completes the whole transaction. Now let's talk about 3 very important signals on the I2C bus: the start, the repeated start, and the stop conditions. So first, when the bus is idle, the I2C hardware can initiate a transfer by generating a start condition. On the waveform, you'll see the SDA line transition from high to low while SCL stays high. That transition is what defines a start condition. Next, in some applications, the master may want to keep control of the bus and continue with the next transfer without ending the current transaction. In that case, it uses a repeated start. A repeated start looks almost the same as a normal start, except that it happens without a stop in between. And finally, when the master wants to finish the communication, it generates a stop condition. On the waveform, that's SDA going from low back to high, while SCL remains high. That transition tells the slave that the entire transaction is complete. So, to summarize, a start kicks off the communication, a repeated start lets you continue transmitting without releasing the bus, and a stop ends the transaction. These three signals form the basic control flow of an I2C operation. Now let's take a look at the acknowledge bit, or what we usually call the ACK in I2C. After every 8 data bits are transmitted, the transmitter will release the SDA line and wait for the receiver's response during the 9th clock cycle. At that moment, if the receiver pulls SDA low, that means ACK, which tells us the data was received successfully. But if the receiver leaves SDA high, that becomes an NACK, meaning the data was not accepted, or the receiver wants to stop the communication. Depending on the direction of the data flow, this ACK or NACK can come from either the master or the slave, whoever is receiving the data at that moment. So how do we know which direction the data is moving on the low power I2C bus? In the diagram on this slide, the blue sections represent the data sent from the master to the slave, and the white sections represent the data returned from the slave back to the master. In an I2C transaction, the master is always the one that initiates the communication. And based on the read-write bit, we can immediately tell the direction of the transfer. If the RW bit is 0, that means the master is writing data to the slave. If the RW bit is 1, then the master is reading data from the slave. So with that bit plus the bus direction definition, it becomes very clear which side is sending and which side is receiving. Here we have an actual I2C signal waveform. Every bit on the SDA line, including the address, the read-write bit, and the data bits, gets latched on the rising edge of SCL, or while SCL is high. For example, if the master wants to write data to the slave, you'll see the read-write bit is 0, indicating a write. If the master wants to read data from the slave, the read-write bit is 1, indicating a read. By looking at this waveform, we can clearly see who is sending data to whom and the direction of the transfer. Next, let's talk about the control registers of low power I2C. These registers have several important control bits that manage the operation of I2C in master and slave modes. First, there's STA, which is bit 5. When we set this to 1, the low power I2C will generate a start or repeated start signal, kicking off a communication sequence. Next is STO, which is bit 4. This bit is used to generate the stop condition. In master mode, setting STO to 1 tells the low power I2C to end the current communication. Once the stop signal is successfully sent, the hardware will automatically clear this bit for you. You don't need to clear it manually. Finally is the SI, bit 3, which is the interrupt flag. Whenever the low power I2C status changes, like after data is sent or an ACAC is received, the hardware will set this flag to 1. You need to clear it manually in software by writing 1 to it, so the controller can proceed to the next operation. Next, let's take a look at the status register. This register lets us see the current operating status of the low power I2C. It actually defines up to 26 different status codes, and each one represents a specific stage in the I2C communication process. For example, when the master is writing data to a slave. First, you'll see that the start condition has been sent, which is represented by code 0x08. Then, the master sends the slave address along with the write bit, and once it receives an ACK from the slave, the status code changes to 0x18. Next, as each data byte is successfully transmitted and acknowledged, the status code shows 0x28. If the slave responds with an NACK instead, the code switches to 0x30. Finally, after the stop condition is sent, the bus is released and the communication sequence is complete, which is indicated by 0xF8. By keeping an eye on these status codes, you can clearly follow along and track every step of the I2C communication process. On this slide, we're going to talk about the auto operation mode block diagram for the Low Power I2C. You can think of it as having three main parts: the trigger source, the auto operation circuit, and the low power PDMA transfer with the wake-up mechanism. Let's start on the left with the trigger source. The low power I2C can be triggered by various sources, like the low power timer, the tick timer, or WKIO signals. You can select which source to use through the TGRSEL register. Once the trigger condition is met, it generates an auto operation trigger, which starts the auto operation circuit in the middle. And if you set TRGEN to 1, it enables the trigger function. The middle part is the auto operation circuit. Based on the auto mode settings, it decides whether the current operation is a write command, a read command, or a random read command. On the right side, once the auto operation circuit is active, it works with the low power PDMA to move data for both TX and RX. This generates LPPDMA requests, and the hardware automatically transfers the data in and out, so the CPU doesn't need to get involved. On the bottom of the diagram, you'll see the wake-up event generator. During auto operation, if certain events occur, the system can wake up the CPU. For example, if a NACK is received and the NACK WKEN bit is enabled, the CPU will wake up. Similarly, if a reception completes and RX WKEN is set, the CPU will be woken up. And if a transmission completes and TX WKEN is enabled, the CPU will also wake up. In auto operation mode, there are actually three main operating modes. The first one is write command, where the master sends data out, so it's essentially a mastered TX operation. The second mode is read command, where the master reads data back from the slave, which is master RX. The third mode is random read command, which is a bit special. It's a send then read operation, with a repeated start inserted in between. The main difference between these three modes is the direction of the data, and whether or not a repeated start is inserted between transmission and reception. One very important thing to note here is that in auto operation mode, TX and RX must use separate low-power PDMA channels. If you try to use the same PDMA channel for both TX and RX, they'll conflict with each other, and the whole process won't work. So remember, assign one channel for TX and a separate one for RX. In short, auto operation mode is all about letting the hardware and PDMA work together automatically. This way, the CPU hardly needs to get involved, saving power and time and making the data transfer much more efficient. Next, we'll go through the operating flow for each of these three modes in detail. Let's start with the flow from master transmitting data. Before entering auto operation mode, there are a few basic settings we need to do. First, you need to set the trigger source. For example, if you want to use the low power timer, tick timer, or WKIO as the trigger, make sure you select it first. Then, turn on the clock for the low power I2C and enable auto operation mode. If you want the system to wake up when a NACK is received during the address phase, you'll need to set the 7th bit in the auto CTL register of the low power I2C. On the other hand, If you want the system to wake up after all the data has been transmitted, you'll need to set the 5th bit. Finally, there's TXCNT, which indicates how many bytes you want to transfer in total. In this example, we want to send 3 bytes, so TXCNT should be set to 2 because it counts from 0. Next, let's go over the flow for master reading data. First, just like with transmitting, we set the trigger source, then turn on the clock for the low power I2C and enable auto operation mode. If you want the CPU to wake up when a NAC is received during the address phase, you'll set the 7th bit in the auto CTL register. If you want the CPU to wake up after all the data has been received, then you set the 6th bit instead. Finally, RxCNT is used to set how many bytes you want to receive. In this example, we want to receive 5 bytes, so RxCNT should be set to 4 since it counts from 0. Finally, let's talk about the random read command, where the master first sends data and then reads data back. Before using random read command, there are a few setup steps we need to complete. First, select the trigger source, for example, a low power timer, and configure the low power PDMA to automatically move data. Don't forget to enable the low power I2C clock. Next, we move to the auto CTL register. There are 3 main points here. First, select the trigger source. Second, set the auto mode. If you're following a standard I2C repeated start flow, set it to 011. If the device requires a stop before restarting the transfer, set it to 100. Third, set TRGEN to 1 to enable the trigger. For the wake-up mechanism, if you want the CPU to stay asleep until the task is complete, set RxWKEN to 1, so the CPU wakes only after all data is read. It's also recommended to enable NACKWKEN to immediately wake the CPU if there's no response from the slave. Finally, set the data length for transmission and reception. TXCNT specifies the length of the register address to write, and you should set it to 1 less than the total number of bytes you want to send. RxCNT specifies how many bytes to read, and it also should be set to 1 less than the total. One important note, in random read mode, RxCNT must be at least 1. Otherwise, the flow won't execute correctly and the data won't be received properly. Here we can see an actual waveform. In the top image, the auto mode is set to 011. After the TX phase finishes, the master does not send a stop. Instead, it immediately sends another start. This means the I2C bus is not released, and the master starts the next transfer right away. On the waveform, you can see that the 2 start signals are back-to-back with no stop in between. Now look at the image below. Here, the auto mode is set to 100. After the TX phase completes, the master first sends a stop to release the bus, and only then sends the next start. On this waveform, you can clearly see the stop and the next start are separated, showing that the bus was released before the next transfer began. That wraps up our training session on low power I2C. We also have a video showing example code using low power I2C, which you can find in the video list. Thank you for watching, and if you'd like to learn more or have any questions, please feel free to reach out to us.